So let's characterize these intermodulation products so that we can quantify them and have an ability to characterize how good or bad a system is with respect to creating these intermodulation projects. So we generate a test signal for our intermodulation characterization. And what we do is we use a test signal that simply has our two input signals that we used before. And what we've done is we've made them have the same amplitude, right? And I've just defined omega 2 equal to omega 1 plus delta omega. And that's for convenience that we'll see later. Really, the only caveat that's changed is we've said, okay, they've got the same amplitude. And so here's our assumptions. And this is called a two-tone test because we're putting in basically two tones with the same amplitude, and we're going to measure the intermodulation product that comes out. And so I want to take for a second and go back to our expansion that we had before. And I just want you to look at this aspect right here and this aspect right here for the two assumptions that we have. All right? Okay. And the one assumption was that A1 equals A2. And the second one is that omega 2 equals omega 1 plus delta omega. So let's look at these two with that. So our output is going to be equal to alpha 1 plus 3/4 alpha 3 plus 3/2 alpha 3 times a cubed times cosine omega 1 t. Now, why I was able to do that? Well, this A1 is the same as A2 is the same as A1, so I can just multiply this in here and multiply this in here. I get a cubed, and I can just pull that up. Likewise, I can do the same thing for the second one, alpha 1 plus 3/4 alpha 3 plus 3/2 alpha 3 a cubed cosine omega 1 plus delta omega. Okay? T. And I can simplify this if I need to. It simply is going to be 9/4 alpha 3. Okay? So now let's go take a look at this down here, this first one. So plus, I'm going to have 3/4 alpha 3 a cubed cosine 2 omega 1 minus omega 1 minus delta omega, where I've just substituted in this here, right? And this is going to give me omega 1 minus delta omega. And then I can do the other one, 3/4 alpha cubed a cubed cosine, and this is going to be 2 omega 2 minus omega 1. And this is going to be 2 omega 1 plus 2 delta omega minus omega 1. And this is going to then be omega 1 plus 2 delta omega. Okay? So if I change my colors real quick, I'll just highlight these. I have this term is there. This term is there. This term is there. And then finally this top term is there. All right, so that's how we've derived it. If it looks a little messy, that's okay. Watch. We can clean it up. I wanted to just show you how we've gotten to this point where the 9/4 comes from, where the plus 2 delta, and where the minus delta comes from. And so now what you can see is we've got omega 1, right? And we've got a tone at omega 1 plus delta, that's that one. Omega 1 plus 2 delta, there we go. And here is omega 1 minus delta. So you can see, got that, Got this one, and then finally that one there. Okay. And we've just assumed that we've filtered out everything but these frequencies. So you can see we've got everything there. And because the delta omega was fixed here, the frequency separations are nice and clean. And before we reach any kind of gain compression, the main tones grow with A. So these increase with A, and these two increase with A cubed. Okay, and you're saying, but wait, doesn't the main tones, or don't the main tones, have an A cubed component? They do. But what you need to notice is that we're assuming, first of all, alpha 3 is very small, but we're also assuming that we're well before compression, so the amplitude is actually small. So if I've got A and an A cubed term, for A being very small, I basically can ignore this second term because this dominates. Here, however, A3 is the entire term, so I can't ignore it, and this dominates for these coefficients. So what we're saying is, if you think about it, very small signals, we're dominated by the voltage is going to increase with A for the main tones and with A cubed for the side tones, even though the side tones are very small. Now, you probably can imagine from previous modules, the problem here is that these harmonics start to grow faster than the main tones at a small level. Obviously, once we start to get to a big input level, we can't ignore this tone, and we've got to take into account the A cubed that's there. But let's just go back and look at small inputs and the trends that happen. So if you recall from the previous lecture, this is a P in, P out plot where we're using 20 log of the voltages. Okay, so it's a power plot, but if you remember on the previous slide, we were talking about the voltages, and so the difference there is whether we're using 20 log or 10 log. So the top line right here shows the power of the main tone, and we know from before that its slope is just going to be 1, right? And the gain of the amplifier is this offset. Okay. This line, okay, it shows the IM3 products. If you notice right away, its slope is 3. If you're wondering, well, why 3? Well, remember, if I take the log of, let's just take a number b cubed, right? We're going to end up with 3 log of b, right? So as my input moves 1, my output's going to move 3 because of this prefactor. And remember, we're looking at the third order product, and that's why there's a cube there. So this line's moving up. Now you notice I haven't shown anything up here where compression happens. We're just looking at small signals down here. All right, and the other thing we look at is that these lines right here tell us the difference between the two. And if you notice, that difference is reducing. And the whole idea behind characterizing intermodulation is to make believe that this trend continues, and eventually there's a crossing point. Now, what do I mean by make-believe? Well, in reality, before any of this would happen, this would compress, right? So what we're assuming here is that we're at small signals where these are still following the trends of 1 to 1 and 1 to 3, and then we just imagine where are they going to meet. And before we do that, let's just talk a little bit about how these two lines come close to one another. Let's take a look at the difference. So if we measure the relative IM3 to be minus 25 dBc, let's just look at that for a second. dBc, remember that's dB relative to the carrier. Remember that? By definition, the difference is dBc. This is omega naught, our omega 1, and this is 3 omega 1. So by definition, the difference is dBc. And an output power of 20 dBm. So that means our power output is 20 dBm, and we measure a difference of 25 dBc. The question is, what is the difference going to be at an input power of 22. Now it's written out here, but I want to go over it really slowly here. So P1 is increased by 2 dB, right? Because we've gone from 20 to 22. IM3 is increased by 6 dB. Why is that? Because the input went up 1, 2. So this went up 6, right? Because it has a slope of 3. The difference increased by 4 dB. So the new answer is that the IM3 would be equal to minus 21 dBc. Now, here's the gotcha, and I'll go ahead and write it for you. Okay? The difference, delta, changes by 2 dB per 1 dB increase. Okay? So that means if I go up 1 dB, the difference delta, it goes up. It reduces, the delta reduces by minus 2 dB. C in this case, right? So right, we go up by 2, we end up with a 4 decrease. So let's just play that game. If I keep on going up 1, 1, 1, 1, when will these two intersect? Well, if my difference is, let's take our example, let's say my IM3 is equal to minus 22 dBc, right? I know that I lose 2 of these every 1 dB that I increase in input power. So let me just take 22 and divide it by 2, that equals 11. And so that means if Pin increases by 11 dBm, then my IM3 will be equal to 0. And how did I figure that out? I just did it through geometry, by the fact that this is decreasing 2 dB for every 1 dB increase in input power.